But I don't want to
What
lose
you
it.
want?
I don't want to lose it. Shall I keep it with you? Because I don't want somebody will steal it.
Okay. Okay.
Now,
Later on I will give you.
now I'm not responsible.
Okay. Hoş geldiniz çocuklar.
But I don't want to lose it. I don't want to lose it. Shall I keep it with you? You recorded already. I don't want somebody will steal it.
No.
Okay.
Good.
Now later on I will give you.
Now I'm not responsible.
Okay. Hoş geldiniz çocuklar.
But I don't want to lose it. I don't want. Yes, I don't. I try to collect it to astrophysics as much as possible. But the idea is some knowledge in one field, how can be adopted and applied to another? And that's what I think it's done. Well.
Gelin çocuklar.
It seems maybe simplistic, but I think it's never better right?
Astronomi öğrencisinin fizik mi? Astronomi. Sizlerle tanışmadık dersiniz olmadığı için. Herkes bana yeni geliyor. Sen iyisisin. Kaçıncı sınıftasınız? Birinci sınıf. İngilizceniz var mı? Az bir şey mi? Az bir şey. Tamam. Soru sormaktan çekinmeyin. Türkçe'de soru sorabilirsiniz. Sıkıntı yok. İyice de öyle sıkışmayın. Canım bir sürü yeriniz var. Yani. Sorularınızı çeviriniz, cevapları da iyi kötü anlarsınız. Çevirinizi şeyler yaparız hep beraber. Tolga will introduce to you in English if you want.
You will not know if I understand you. And I will not take it.
Arkadaşlar merhabalar, hoş geldiniz. Ayakta kalmayın. Gelin bakın burada boş bir koltuk var. Hoca gelsin. Sen de birlikte otur. Ha, bilmiyorum. Üç ayağı çarptım. Tamam. 12 yıl önce Çin'deki uluslararası astronom toplantısında hocayla tanıştık. Zaten bir gruptu. İşte belli bir yaştaki insanlar bir araya geliyor, kahvaltı yapıyor falan. Hemen hemen aynı otelde kalıyoruz. Oldukça samimi, sıcakkanlı. Orijinal hoca Polonyalı. Ama Amerika'da çalışıyor, Kaliforniya'da. Berkeley Üniversitesi'nde emekli profesör. Plazmalar üzerine çalışıyor. İyonosfer konusunda da çalışmaları var. Bugün ne anlatacağını ben de ilk kez dinleyeceğim sizlerle beraber. Bütün dünyayı dolaşıyor. Hala aktif, yani resmi görevi bitmiş olmasına rağmen aktif ve kendisine çok teşekkür ediyoruz. Uçak bileti ayın 6'sı gibi görünüyor. En uygun Tolga Hocam. Ayın 6'sına kadar burada. Burada kalıyor. Bizim odamızda kalıyor. Gözlemci odasında. Gördüğünüz her an konuşmaya çalışabilirsiniz. İngilizcesi oldukça temiz ve akıcı. Thank you very much for your talk, and Tolga continue in English because YouTube necessary.
Well, I should just start.
So yeah, I just want to say that.
One people needs English. Maybe he didn't understand my Turkish.
Yes,
Okay.
I have my internal translator.
Thank you.
Anyhow,
Sorry.
thank you for coming.
İngilizce sorabilirsiniz, Türkçe sorabilirsiniz sorularınızı. Gelmişken insanlar dinledik sessizce çıkıp gitmiş olmasın. O çok hoş olmuyor gerçekten. Geldiyse ne kadar istiyorsanız o kadar sorun. Biliyoruz bilmiyoruz diye de hiç düşünmeyin arkadaşlar. Burası biraz böyle canlı olsun. Thank you very much.
I assume that you can understand me. My accent is much clearer than average American. You can think that I have a bad accent in Turkish. I talk in Turkish, and it comes as English. But altogether, I would like to describe the main part of my topics. Some physical processes at one region of science. How can it be sometimes less successfully applied to another field? And what can we learn about it? So basically, I prepare something for beginning of undergraduate. I will describe the basic stories of physics and enter the plasma part, which is the essence of this. Most of you don't never heard about it. And in the simplistic way, from time to time, I will insert something more profound and more important. Since I learned already how to operate this device, this complicated device, I press it. So I don't know if you have, probably in Turkey, you have never seen Aurora. Or probably in Turkish it will be Aurora, but in many languages.
Very rare. 2 times we saw.
Yeah, and you call it Aurora.
In Ankara, and maybe some part of North Turkey.
Yes, I know that there was in Japan, even once, but it's you need to be close to the north or south pole. Okay, I don't know to waste time, so I will jump a little bit faster. So my question is, what can we learn from Aurora's observation about processes that other magnetized configuration? And what are the implications? And I will bring you at the end, if I have time, to strange stories of the beginning of our solar system and maybe some end of the solar system, and everything is connected to the same story. So it sounds interesting. Let's see if everybody knows, assume from high school, we have the planets encircling the sun, and by the way, each plot that I show is can be by itself a topic of a talk or maybe a class. And then I brought it here. When I was a student, I saw the first time the Newton law, and sort of I had strange question which I don't answer very good answer today. Why is it r to the square? If it was r to the 2.6, would it be different? R to the 3 is probably the wrong answer. And the answer is that it's magic. And think about it. And when you hear something, some statement from somebody who tells you this is the one, ask yourself, be critical. It's always good. This was amazing that he found something like that. But I just reminded myself, my student here, some of them wanted to show. Okay, you can read, as you see, the numbers are clear. The sun, planets around it, some ratio. You see, the Jupiter is about 1/1000th of the sun, and if it was 8%, probably you remember something from this, 8% of the mass of the sun, it would start nuclear reaction. That's an amazing story in the 19th century, what happened there. I'm jumping. And then the same way, from the same law, we found that in our galaxy, there is something strange happens. There are stars, it's over, you see the year. Year is here. I will do it. And then there's movement of stars, we observe them. Essentially, somebody got a Nobel Prize for this observation. This is two-dimensional projection of the three-dimensional motion. And you can see that seems, you see the cross there, the plus, and it seems that there is something there. And this was really the final proof that there is a black hole in our system. The same law that applies to our planets applies on the bigger scale and almost any scale. From the point of view of gravity, one of the main forces. And then the same way, like the microscopic world, the fantastic model of Bohr, which essentially say that electrons, like electrons, are going around the nucleus, which is made from nucleon, meaning neutrons and protons. And once you apply some enough power to these electrons that they can bonding becomes negligible, they can get out. And this is that. Plasma is essentially fluid, like water, except that the interaction between the ingredients is not van der Waals process, but electromagnetic. And the movement of charges, they attract each other or repulse each other. Movement of charges causes currents, which cause magnetic field, according to Maxwell. Charges themselves cause electric field, also according to Maxwell. And the electric field and magnetic field affect the motion of the particles as they move, and then they create the fields, and the fields affect the motion. Look at the interesting field. Okay, everybody knows about purity. There's something else people never pay attention. All these elements, they are, first of all, you know about isotopes, when the weight of and it's important for my talk, the weight of the more neutrons are in the nucleus, and that's why they are of this sort. I will talk about some of them. And there's also another thing that is missing here in this, usually in the Mendeleev table, it's called the Mendeleev periodic, are the charge states as we observe them. Because the iron, and we see that the sun in normal time is about +10, +12, +40 charge, meaning it lost several electrons, is ionized. But in some flares, it can be 22. And this is important. So it can be helium-4, helium-3, it affects it. And here you can see the game which starts. And in relativism is crucial. Charge to mass. It has some crucial effect on the behavior of these ionized particles. So, in such a case, I must say, because I'm working now in sometime on this, there's another derivation. Before anybody knew about atoms, Lord Kelvin devised a method. He did not know anything, but amazing. That essentially the different elements he knew, oxygen, nitrogen, magnesium, they knew about them. They differ by some geometry of the structure. Sentence to topology, if you want to study something like that. How it is confined in space. He's completely wrong. It's completely wrong. It's a amazing idea. And even today, in some aspects of string theory, they try to revitalize. There is so-called sky nodes and other things. So, just wanted to tell you, don't be afraid to be wrong. You can be famous. Okay, Aurora Borealis. Here, now each sentence is essentially talk. So what is this? These are accelerated electrons flowing along the magnetic field, and they approach our beautiful planet. They hit denser plasma. When the density is large enough, there's a probability that they will excite the changing momentum a little bit, excite some of the electrons to higher level, and then after delay, because it's partly forbidden transition, you can learn some from atomic physics, so it takes some time, actually a second, it decays back. And as it decays back, we see these beautiful colors. Some of them are in nitrogen, there's a little bit of reddish on it, hydrogen. And the point is that the amount of power, if you calculate it, is 1,000 megawatts. It's a good power station. And spent 20 seconds. Years ago, some senator from one of the states of the United States had this idea that he will harness, we use it, in order to create electricity. Sure, that's it. It's nonsense. But they got a lot of funding to establish fantastic department. So not everything has to be clever in order to get funding for research. Okay, aurora from ground. I will skip now a little bit. Aurora australis is the same aurora, but on the other pole. You know, those people of Australia, they go on their heads, but they have the same magnetic field. It's an improper statement. Here's a remote observation of aurora from satellite, and you see that these are the electrons which hit the dense ionosphere and cause these emissions. It's several processes. There's also something interesting. If the density is large enough, electron can go very close to the nucleus, very close, and then form X. The same X-ray when we go to a doctor is here. And the sun is much better because the fluxes are large. So going to doctor, going to the sun, there's some similarity. And now if I get this talk 450 years ago, I would say we solved the problem. In 1570, they knew everything. You see, the houses, beautiful houses. There are some stars, and there are some candles. That's what we see. You think that this is correct? I think that most of you would say that it's completely wrong. But it's genius. You can say that they already knew that there are some magnetic fields. So, since then, I can say that 450 years ago, I did this talk, we stopped here before we did. But we are today, so instead of cartoon like this, what happens since then, especially in solar physics? A little bit exaggerating, but not enough. Most of the research is drawing cartoons. If you look at even any book, you can see cartoons, pictures. Okay, this is cartoon of the magnetosphere. Each area I can give a talk, and I want to emphasize the auroral oval. So these are the field lines which are somehow today we know that generally that at the magneto tail, which is here, there's some reconnection, some process in which the magnetic field is changed. Enormous amount of energy is translated as waves. These waves accelerate electrons. These electrons go here, hit the atmosphere, low atmosphere, and you see the beautiful aurora. End of the story. Now we have to start the research. A jovial magnetosphere. You see almost the same picture. There's the tail. This is today. The difference is that this is huge object. It rotates in 10 hours around, and you can go further to something that rotates very fast. Pulsar is essentially fast Jupiter, very fast. I exaggerate, but if I just present it, and those who know about it will think I will go further. Okay, Jupiter is essentially slow pulsar. There's some volcano, another topic, the ions which are, for instance, emitted from one of the moons, Ganymede or Europa, and they perturb the field line and cause these fluxes of electrons. And then this is the aurora. This is million megawatts. It's much stronger than our planet. What else we see? Saturn. There is from geyser, which cause us to see aurora. Here's the aurora at the Saturn. There's Ganymede, one of the moon of Jupiter. It has its own magnetic field also. It's we see the aurora. Neptune, tiny, but has aurora. It's solar corona. We saw it a few weeks ago, a better one than this. Okay, here I have one introduction, which most of you will remember. How the charged particles behave in the present day magnetic field. In high school, we learned that it moves around somehow. You remember there, so that's much important. So there is one motion of the gyro motion particles in the constant magnetic field will behave like that. And there are some, I will say about it, some invariants. In the non-constant magnetic field like ours at the Earth, there's additional mirror force, so-called mirror force, the particle which enter the stronger magnetic field, feels repulsion and comes back. And this is called, this motion is observed, it's bounce. On top of it, when particle comes here to one of these junction points, it can easily switch to another field. And as a result, it will move electrons one way, ions the other way, and there is another drift. So that this is the drift. These are three motions. In mathematics, we know that for every periodic motion, there is some additional coordinate, the adjusted coordinate, and there is typical frequency. So in our planet, this is about a fraction of a second, this motion. This is about a few seconds, and this is maybe hours. So we have a mathematical structure in which you can divide different time scales. When there are different time scales, we always make famous approximations by ignoring one or averaging over the others. If you study applied mathematics, this would give the right point. And then when they exchange energy, essentially the particle can lose energy when the adiabatic environment is not preserved. So changing of energy, losing or gaining, is essentially a violation of adiabatic environment, which is very important property in the trajectory in the stochastic structure. I'm using some fancy words because I don't want to enter it, but you just for the proper description. Okay, this is the same what I say about adiabatic environment. The gyration, bounce, and drift have their own, and this is a simulated portion of particle around our planet. Here is gyration, is bounce, and this bounce it goes to another field line and another field line, and it moves like that. And this is very nice track particles. You know that about 30,000 kilometers from Earth, there's a region of so-called radiation belts when electrons are trapped. And they exist there. We found them only in the late 60s when we started to launch satellites and we went through this region. And this essentially brings some very interesting mathematical problem of trajectory in space, and how to explain them, how to utilize them. Here's a beautiful experiment from UCLA when particles were bouncing, and then it went to the another field line. Exactly what I said before. And there, this is the essence of purpose of creating nuclear reaction. We build fascinating magnetic configuration and allow the particle move such that it will be confined, it will not be lost. There's a lot of theory for 50 years now. We work on this, and here is the first big example in the so-called tokamak in Princeton, and then this was the structure of the toroidal magnetic field. Quite becomes complicated when you want in the big scale structure confine particles that they will not run away. Because if they run away, they hit the walls, and because there are a lot of problems. And here's the structure, the so-called tokamak in Cadarache in France, beginning of construction, just to show you, just to fascinate you by the dimensions of this building, and these are two guys inside the magnet. It's meters, meters is the magnet. And so now this brings me to my next point. Different worlds have similar processes. This is aurora. This is corona. What is this? These are also electrons, which in the upper part of the corona, when somehow energized, they move. We know they have a very small mass, so they are confined with the magnetic field. They move inside, and when they hit the lower, they emit this stuff. They emit also fantastic X-ray, and here's another process which some of you probably know about coronal mass ejection. This is a chunk of matter of 10 to the 30 grams, 10 to the 50 grams, then some is 10 to the 60 grams, moves with the speed of 2,000, in rare cases, 3,000 kilometers per second. So this is like a nano supernova. And we see it all often in our system. Supernova has 10 to the 51 error energy. This has 10 to the 33. Some numbers. So it's a big event. And here, next one should be something nice. This is the real picture of coronal mass ejection. So better not to be there, but people survive it all. I can tell you more about it. We're there in corona, and what if you know the magnetic field is going together with the rotation of the sun. As a result, the magnetic field makes the shape of the ballerina sphere, that dancing. In the video, you see some planets there. Okay, 5 years ago, first time in human history, we launch satellite, which is close. Gosh. That is NASA program. It will reach, essentially, it has been supposed to encounter Venus next month or something like that, and it will reach 9 solar radii. I will show you something. And we are now in the distance of 220 solar radii. Solar radius is 700 kilometers. We are in the distance of 150 million kilometers. 220 times sun. And this satellite will reach already 10. Now it will go to 9.5 solar radii. Revolution in ability, because it has shielding, the appropriate, can give the whole lecture how the technology allows that it's not in operates process. What the instruments are in perfect shape. So here it is. I was in France. This was there. So before I was 9 o'clock, I think, in the morning, but this was at 3 at night. And we saw this launch, which I always like to remind myself. Here it is. And this is the structure of this, of the trajectory. So what is about the trajectory? This is Earth. Will go approximately as we saw before. We launch it first time somewhere. I will show you in a moment some movie. It touch when it encounters Venus, which moves also. They exchange small amount of energy, and then the trajectory becomes more elliptical. So it will go closer to the sun. Times passes, few months, it encounters again Venus. Venus is the best one, which is strong enough. And every few months, every year, it gets changes the trajectory. And here I would like to make the famous movie, if you can find it. Here it is. I will run it. So this is the Parker Solar Probe, which we launched. You can see it here. From time to time, see, it goes. These are the other solar. And here Venus is closing. Something happened. And it changed the trajectory. And it goes on. By the way, those who are in good side, you can see the date. I can see it on the computer. So I don't know. This is 2021. Well, it's broke, the pandemic started. Okay. So you can see. So it goes on and on. Every time it changes. I will run it 2 times. You see how the same law of gravity applies here, and it's an amazing example of the structure. Mercury does not affect Venus. Something the pigment. So what year are we now? 24. Here it is. February, March. Look, here we are. Okay. Now it's the future. You can see the future. And in the future, I forgot to tell you, there was another satellite, which is orbiter. Do you see it here already?
Orbiter.
Yes, there's orbiter here. And this doesn't go that close, but it is off the galactic ecliptic plane. You know, there's astrophysics, you learn problem. That most of the planets are almost in one area. Amazing story. Another story. Okay, so the point is that it goes, and now the only thing is what happens next year when it reaches this, because we have to justify the funding from NASA. And this is another aspect of life. Anyhow, please, you can see it later. Where can you retrieve myself? I'm here. Yes. Okay. I will skip now. This is the orbiter in February 2020. They launched the other one, and this brings me to the end of the accelerated end of my. It's almost one. Now I start. We go now 13.5 billion years ago. Big Bang, not a nice name, but it's correct. Okay. And then this is the Big Bang because it's abundances. We know extremely well the cross section at these high temperatures, and this is some people claim that this is the most important finding in physics, in modern physics. So, besides hydrogen, in these first 100 seconds, we form helium-4, deuterium, helium-3, lithium, and a little bit maybe beryllium and boron, which are the these are the elements which started our existence of this universe. I exaggerate a little bit, but who knows? Maybe that's the right word. And this everything depends on the density of the baryons, ordinary matter. If you this will essentially you can see it here. If I got this line, from other reasons we know that the baryon, the regular matter in the universe, is only 4% of the total mass energy, I would say, in the universe. Only 4%, that's what you can see. And besides it is the famous dark matter, some 20-some percent, and the exotic dark energy, which we are still looking for. And I'm not going to talk about it. So this is the description of this routine. I want to emphasize only one aspect of this individual. And it's a fantastic theory which gives the amazing story that at the beginning of the universe, the primordial, original helium mass fraction, helium to mass of helium to hydrogen, to total mass, is about 1/4, 8% by number, and primordial, I can explain it later. Primordial ratio, this is the important, that helium-4 is about 5,000 more than the helium-3. And here is the question. If we can find some place that this is a really primordial, it's not happened over 30 million years. If we can find it, then we can put this number precise. And if it's make it precise, we can find really what should be the total density of matter at that time, which is one of the crucial numbers. We had about 4%, but it's not precise. So is it possible? So then the question is, okay, it happened 30 million years ago, it's something happened, but in many cases not that much. So I raised the question, I posed the question, what should we do with this? And I will start now running. I will skip George Ganoff's story. And this is again the same helium, helium-3, lithium, deuterium. Each one of them is a fantastic story by itself, is a saga of stories. There's also galactic evolution, and galactic evolution, we know what I want to emphasize is that stellar average value of iron to oxygen is about 10%. That's elements. We understand the evolution of the electricity in the average sense. Observation of helium-3 to helium-4, in many places, we found exactly the verification of this number. It's really something 1 to 5,000 in many others. Now comes the question. 40 years observation, suddenly we see it over and over, and with better instrumentation, it depends. Then suddenly in flares, specific subset of flares, but most of them, in flares, when we measure the ratio of helium-3 to helium-4 energetic, which are excited, emitted from the sun, these numbers is You see, helium-3 is larger than helium-4. Helium-4 is helium-2. This was 40 years ago, and it was not explained. At some moment, I think it was explained, but this is my story. How with plasma physics, I can go into this. These are other places. Helium-3 is still smaller than helium-4, but not 1/5,000. And now there are also cases when you see helium-3. Helium-3 is this, strong more than helium-4. Also suddenly iron, this one, is larger than oxygen. And there should be less, should be 10 times smaller than the same. So there are some anomalies. The anomalies always are interesting because to explain them. This is the amazing case. We had a paper about it just recently, that helium-3 was more than hydrogen. So what happens is there is some effect that enhances helium-3 and allows it to go out of the sun. And it's not nuclear physics. Because if nuclear physics was there will be another element which are effects, and we don't see them at all. So there must be some purposes. And I don't know how to continue fast enough. I will skip it. Here I wanted to show you each one dot is one atom, one ion, which of them. Each one of them we observe with a satellite. So Big Bang gives our huge difference between helium-3 and helium-4. In passive flare, it's reverse. Stellar revolution is 0.1, in passive flare is 1. And now I will run as much as possible. These are the data. So you see the aurora. You see the aurora, and you see also electron fluxes, as I described them. These are the electrons which hit the aurora. And the model will be that some electron flux, which are here, and they excite waves, which at the moment, this is the beam of the electron waves. These are the waves. Let me see. So there will be electrons which interact, and they bring elements from the ionosphere, and they interact particularly with helium-3. Why is it so? Helium-3 and iron, and then xenon and other elements. So if I go backwards, solar corona and terrestrial aurora have some peculiarity, have something special. Go back. These are the parameters which are in class. There's some plasma frequency, gyro frequency, which we're talking already, and beta, and beta. And there, as we observe the aurora, we see that the waves which are emitted from these electrons, and this is another story, how they are exactly between the F is instead of the omega, the gyro frequency with hydrogen and helium, something in between. If there was helium-3, which has the special ratio of Q over M, charge over mass, in between, it will be here. But at the Earth, there is no helium-3. So therefore, the statement is, we see these waves, and they cannot do too much. On the other hand, in the corona, this process of Landau damping is the appropriate one. What is Landau damping? Landau damping is is exactly when you go surfing. You are at the right velocity when like the phase velocity of the wave. But in waves, there's also electromagnetic wave, electromagnetic field, which together with particles excites them and energizes them. So it's energized and it's moving. And this is the essence of acceleration. I already talked about it. So, in both terrestrial aurora and solar corona, some of the numbers, all the numbers are different, but the ratios which play the role of the strength of the interaction are very similar. We know that there are intense fluxes of the sun. We know that it is in situ at the aurora, and then this picture describes exactly what I wanted to say. I reverse it a little. So bottom line is that here in the sun, we have all these elements, hydrogen, helium, doubly charged, and waves in between. And who is then in between? There's this. What is helium? See, is the helium-3. That's why helium-3 is a natural ingredient which can be accelerated by this process. But more than that, if we go further, if you say second harmonic, which also can do it, and I did it on this analysis, we can accelerate some specific elements of iron, and maybe even ultra heavy, xenon and krypton. So this gives me a lot of gains, which elements will be at what temperature, and from the statement of knowing the temperature from Saha equation, I can say that between 4 and 6 million degrees, this will be the best acceleration. Another 10 minutes.
We have
I can have time
we have time. Yes.
because I delayed, retarded. So can I have some more time?
It's about 40 minutes now.
So I can
We are
go
going
now.
very fast.
I thought that I'm limited, but now.
Yeah.
Yes. Okay. So anyhow, so you can see that, okay, so then I can describe. If you have equilibrium at given temperature, you have all the atomic physics. Electrons are charged, some of the electrons are emitted, and the iron, as magnesium and others, can be charged to different states. And then, when they are interacting in this way, either the first harmonic of helium-3 or second harmonic of iron and others, then other elements can be excited. And they will. So, according to what we observe in the interplanetary medium, we can say what was the temperature of the sun during this period. And this is also something nice and be wrong, but these are a way of analysis. So this essentially what I wanted to emphasize here, that at some moment, and then I emphasize it because it's brand new, sulfur and silicon, some also enhance. It should be one before. Silicon is enhanced. And the point is that last month, we found in one of the events by the solar orbiter last year that silicon was enhanced very significantly, which means in the old picture, you see, I did it 20 some years ago with silicon graphics, can be all operative. I hope the essence is clear. So here it is the observation of recent April 23, and here it is silicon and sulfur excited to large area. I'm almost done. Mathematics is less important. Simulation is how the particle behaves, which is also cute. You can see the parallel velocity, energy up to 14 MeV in this simple. And I will leave this part as sort of problem quasi-solved. And then Aurora, which is excellent laboratory for plasma, they can be applied to beyond Aurora. And I will go now very as fast as possible into different modes, different topics. Aluminum-26 as a clock for early solar system. Why aluminum? First of all, aluminum is 26 is radioactive. It has, I will show you in a moment. It has energy, which is extremely important for heating of the solar system before the formation. And it brings me the story of meteorites. What we see in meteorites sometimes can give us information what happens in the first fraction of a million years, 4.5 million years ago. So, first of all, the aluminum-26, this is what we see. It operates everywhere in the Milky Way. It has the significant, very sharp 1.8 MeV line. I will leave it as a dictionary because this is the story. All the meteor theory is here. What I want to observe, to emphasize out of this, is that aluminum is radioactive and it decays into stable magnesium-26 with a half-life of over 7 million years. Now, we observed too much magnesium-26 in so-called calcium-aluminum inclusions, which are the oldest pre-solar silicates and refractory minerals. And I'm using words which are from different topic of research. That's what the people are out there. So there's too much magnesium in these first oldest parts of the meteorites. And here's a picture. This is the calcium aluminum inclusion in the controls. And another picture. And the explanation, galactic ratio is generally 26 to 27, is of the order of 3 to minus 6, while in calcium aluminum is 10 times more than 10 times large. This is the problem. How to solve it? There are many ways where I will not say there's, you heard probably lead dating is essentially gives out this. In control, we draw some line from data, and from this we observe that it was 4.36 billion years ago, while this was 4.567, a little bit older by 4 million years. Okay, so that's the essence that people claim this calcium aluminum inclusion. If you observe the small speckles, they are the oldest part of our solar system, and they have some strange thing. They have too much magnesium, and the magnesium somehow could not be. If there was only supernova, there was a supernova. But if there was only supernova, then we would see also many other anomalies, and we don't see that. So I will go fast over this, and there are all observation. We find it. And then possible solution, external Lugnos event is proven insufficient. So my story is, it's not that there's a lot at the beginning of the active solar system. There's a lot of intense helium-3 fluxes which we know today measurements. These are the energies which were not so well observed, forming aluminum-26. And this aluminum abundance increased before solidification, due to interaction with helium-3, resulting in magnesium-26 in there. So this is my solution. And I don't know if I should go to another topic or say that I will leave the other topic next time. And the other topic is, I will just present it, is this astrophysical helium-3 problems. There's too much helium-3 in some place and nobody knows where it comes. And I claim that in the planetary nebulas, these are the specific events when helium-3 was formed due to the same process. Now, I will just go fast this data and I will skip the details. Planetary nebula, this is the helium-3 which they observe, and we'll leave you with a plasma solution that a magnetically active star is able to increase substantially its nebula with helium-3. So Aurora, excellent laboratory for plasma processes many years ago and many years in the future, and today these are the examples that they touch towards the end, and this is my thanks.
Yeah, okay. Thank you very much for this nice talk. Okay. Yes, go ahead.
Okay.
Any
If you have any comments, any questions which I cannot answer, I will ask them. Or any
I have one. Which type of flares were you talking about?
in the literature, they are called impulsive flares.
In South.
So these are, it takes relatively minutes to show. They are not the huge flares which the whole part of the sun explodes. They are not coronal mass ejection, which are also exact. And the point is that these flares occur often, they enrich the interplanetary medium in some anomalous elements like helium-3, iron, and they stay there. And now we become satellites, and we observe suddenly short time after that with a good version. So this was curiosity at some moment 40 years ago. Then more and more, generally people agree that the model which I described, which is essentially surfing and energizing, is accepted. That's it. About the meteorites, generally that's okay. About the last helium-3, nobody understands it, so I don't.
Other questions?
Feel free, anything that.
Yeah. So you said you can basically determine the temperature that the plasma has from the abundance of the elements you
Yeah,
get.
you know, it's a game.
I just want to see if I really understand that idea. So it's the idea that the temperature determines what fractions or how strongly these elements are ionized.
How much they are, what are the chances?
Yeah, so how many exactly?
The temperature changes the charge state because it's an equilibrium.
Yeah.
Jump up, there are tens of processes, double electron. I went through this literature. You can spend your whole life studying it, but there are tables. So the bottom line is that we put 4 million degrees in the plasma and put whatever elements you want. And then you find distribution of charge states. Now, some of these charge states will be able to resonate better with the waves. Yes. The waves come. They resonate in resonance. They are there. You know the picture of the water.
Okay.
Yes. And they will be excited, energized, and get out of this. And we will.
So the only thing is the plasma frequency, the charge over mass ratio.
Charge over
That
mass
has to
ratio.
fit some.
Yes. It's amazing. Like a charge. So Q over N. And I don't know if you encounter it in other fields, but it's probably well known. And it's nice because it's a microscopic effect. This is macroscopic result. But it's always a cross section, two particles in the round. And this determines what happens in the globus sometimes. So I think that this is cute, this analog. Is it completely correct? No. There are some data that say that it was not for million research I claim, and they found it that it was 2.5 million. Okay. Depends. They also don't know because it can be 2 million, 4 million limited part, some hidden part of the sun. And that's what you're right. So,
Okey. Arkadaşlar Türkçe de sorabilirsiniz. Biz hemen onu Google'da da burada, Erdoğan'da da burada çeviririz herhalde. İngilizce de sorabilirsiniz. Yani biraz soru soralım. Aklınıza ne geliyorsa. I explained a little bit Turkish things. Okay, another question from.
Question I had was, you talked about the 1 divided by 5,000. Still about 14 years ago, that is changing, and you said that it was related to the plasma. I didn't understand the relation because I would like to have a little summary.
So, 13.5 billion years ago, something, our universe was created. I don't talk about religion. It's, let's accept that this was the creation of the universe. And we know today very well that helium-3 was 5,000 times less abundant than helium-4. And then most of the universe didn't change that much for all these years. Because most there are other reasons. I don't know. But in the flares, the energetic helium-3 is more abundant than helium-4. So what happened? There's a field line. I'm the sun. These are the field lines. One of the field line is agitated. Reconnection to the world. Energy is going into this. And then there was also changing the electrons, which I described. Electrons are energized, they come in and they form waves. These waves, at some moment, interact like this surfer, interact with all the particles that they can. And it interacts mainly with helium-3 because charge to mass ratio is just such that it allows the resonant interaction with the waves. Only these particles mainly. So suddenly, all the helium-3, which was here in this field, all of them were energized. A little bit of helium-4. And then all of them got out by some other process. And then satellite observed. And suddenly it observed that there's more helium-3 than helium-4. 5,000 times increase. And I brought one example that there was more helium-3 than hydrogen. So this was one of the, with respect to weight, and this, I didn't describe sufficiently the effect of resonance. But resonance is really something that takes particular particle and energizes it to very high energy. And I show also my simulation of the energy is going down. So generally, helium-4 is more abundant, much more. These events, helium-3 becomes very abundant, and then this brings me also to all the other stories about the meteorites and physics. So I hope you got some idea.
Yeah, this is down because coming 1,000 questions.
Yes, but I will sit down.
Yeah.
So I don't hear the question.
Evet arkadaşlar.
No.
Gelmişken değerlendirelim. Değişik bir konuşma.
It's not question, questions. Tell me that you have something better or you heard something better. No, don't be afraid. I love questions to which I don't even ask. I'm not afraid to say.
And also, when you were talking, you said that in order to explain this abundance of geometry, we would need plasma physics and nuclear physics to report. And you said that there should be another particle with this, like that.
What is the last one?
I think you said that there might be another particle, something that that we need to explain it by using nuclear physics. So what is exactly the idea?
I don't agree to this. But if there was some really nuclear reaction, like in the nuclear power station, no, it's not a power station. Turkey has nuclear power station.
In the establishing now,
Yes.
yeah,
First one.
since some years.
Yes. In America, they were not. And then one of them was sort of small accident. So there was a public relation disaster. And they don't allow now for 20, maybe 30 years to build any more nuclear station. I think that they are getting some wisdom and understand that this is a great solution. So there will be beryllium, boron, many other elements should be formed. There's a whole slew of interaction, which I'm not interested that much in them because I don't know. But I know there would be, it's like in the sun. In stellar evolution, you have to include all the interaction. And we don't observe anything of this sort. Only helium. So, there was a big debate about it for years. And everybody agrees that there's not enough, you cannot explain. You need some other model. And this model is simple. I have some rule, I don't know if it's correct, but generally, if it's simple enough, it's probably true. I know it. So, because very often there are theories, and they explain it, but then there are new data, and it doesn't explain. So what they do, they massage the theory, and they massage it again, and massage it 5 times, and finally you don't know what is there. So it becomes, when it's simple and direct, it seems very reasonable. Sure. There was some, you see in Stanford, there was some group that they have another waves also. And okay, they have another way, that's not a magnetic ion cyclotron, but some other waves. The only problem is that they don't have any reason to prove that these waves exist. Why I have, because the corona and aurora exhibit the same features. In the aurora, we see the fluxes of electrons, we see the waves, we observe them, we only don't have helium-3 to excite, because there is not. In the sun, there is not small helium-3 that is excited. I will tell you this story. It's not recorded. It is recorded. If you want, I will tell you this story.
For you.
Yeah, that's the idea. Stop the recording. What did he say? 17 that can cause problems.